Earlier during this course, I gave you a small paper, okay, by some people in the medical domain about modeling a simple model, nonlinear model of the COVID spread without any control. So input output, and that's it. And you notice simulating that, if you simulate that model, it's very funny because you realize that everyone is finally dying. Okay, if nothing is done, probably in 40-50 years. Okay, it would be very interesting to build some control on this model, and one way to do that is this way. You see, this is the nice thing about OneNote and about its notebook, that this blackboard is the same from last year. Okay, so I don't need to write this again. I just need to show it to you again. Okay, so we are studying feedback linearization. Okay, so you have a nonlinear system and you build a state feedback. We build a state feedback. Okay, you see here, right? Oh, shoot.
Yes.
Okay, a state feedback. Okay, state feedback. So here you take X. Okay, you build a state feedback such that this whole configuration from V to Y, okay, so this equivalent system from V to Y, this is V, this is Y, is linear, okay? This is what this control needs to do. And this is a very nice procedure, and we showed last time a few examples how to easily build that. The problem is that you cannot do it so easy for any kind of nonlinear system. So you have to have a systematic theory about all these things. Okay, so this is what the slides tell us. Okay, that we need to build some nice structures about canceling the nonlinearities. Okay, this feedback control, this U control, needs to needs to kill all the nonlinearities. Okay, this is the U that we want to build, alpha x plus beta x v. Okay, and finally, the resulting system, the resulting feedback system, is ax plus bv. Of course, for this system, v is usually built as another state feedback, stabilizing this equation, because you need to have a stable equation. And we had these nice examples. For instance, x1 dot is a sine x2, x2 dot is minus x1 squared plus 1 plus u. Okay, and in order to what's the idea? What is the idea? The idea is to write the system in such a way where only the last equation contains the nonlinearities, and from the last equation you should be able to construct the command u, like in this way. You need to find a coordinate transformation such that, here I think it's a mistake. This is z, sorry. This is z1 dot, and this is z2 dot. Okay. Oh no, sorry. These are the coordinates. This is the coordinate transformation. I'm sorry. Now I realize this is the coordinate transformation. Okay. Z1 dot is x1 dot. Z2 is a sine x2. So when you take Z2 dot, you get this equation. You get these equations here. Okay. You get these equations here. And then, how do you cancel the nonlinearities? You build this U. This is very easy. This is a very simple example. How do you do this? How are you going to do this when the system is of nth order? Okay. You also have input-output linearization. Okay. Because usually linearizing the state equations does not necessarily mean that you linearize the output equation. The output equation, which is usually a mapping, a nonlinear mapping of the states, even if it's linear. Look, you did feedback linearization, okay, but unfortunately, so that was state linearization, but unfortunately, you end up with a nonlinear output. So it's again very difficult. It's again very difficult. Yeah, this is because of the x2 you have here. And all your new system is in the z coordinates. So in the z coordinates, even if you do the linearization, you end up with a nonlinear output. So how are you going to tackle this issue? You are doing input-output linearization. You are doing input-output linearization. So you need to hide in the output. This is going to be the idea. Hide the input in the output, the nonlinear dynamics. You need to make it unobservable. Okay? Because in reality you have the so-called you still have the hidden dynamics. If you go back to the x coordinates, this is a hidden dynamics, because in the z coordinates you don't see this. You don't see this. Okay? So if you take some control for input stabilizing to stabilize the output, okay, to get it to some constant value, okay, so you get this relation. So you still have an internal stability problem, okay. So to be able to do this in a systematic manner for any nonlinear system, we need to define a few things. Because we are going to need some functions, some derivatives of these functions, and we talked about them last time. We are going to make a short recap of these things. Okay. So if you have f a smooth mapping, okay, a C infinity mapping, that is, this f of x, okay, from U to Rn, okay, where U is also a subset of Rn, okay. So this mapping is called vector field. It's called vector field. I hope you can so easily associate the English terms to the Romanian terms here, okay?
Yes, no problem.
Vector field. Smooth mapping. I'm going to write it for you. Smooth mapping. Vector field. Okay? Yeah. Okay. So why is it a vector field? Because if you start from x and you add the f of x, you end up with x plus f of x at the end of this vector. Okay. So it's a vector field. This is a two-dimensional idea because it's easy to see things in 2 dimensions. In n dimensions is virtually impossible. Okay. So locally, for this vector field, because usually we have this, and this is the vector field, since this is a derivative, this is tangent. This is tangent to some curve where x is evolving. Okay. So locally, we can say that in a neighborhood, this is, at least here, you don't know what happens in the rest of it, but at least locally, there is a unique curve tangent to any point of x of the vector field f of x. Okay, so we are making some mathematical assumptions so we can define all the notions that we need. We also have the so-called dual space of a vector field, of a vector of a space, of a vector space. Okay. Okay, so these are all the linear applications defined on V that take value in R. Okay, these are called covectors. These are called covectors. Okay, the elements of V star. Okay, so since the V star are linear applications, they can be written as a matrix. Okay, so if V is a vector like this, standing up, W star, which is the covector, is usually a line. It's a line, okay? So W star composed with V yields a scalar product. Yields a scalar product defined like this, okay? So please note that these are all notions of differential geometry. They are not very simple, but they are kind of useful. We also have covector fields, okay, which are defined like this. This is what a Wx looks like. So if you have Fx, a vector field, okay, this is a covector field. This is a covector field, okay? You also have the gradient of some function with respect to all the, so if, okay, so the vector of the lambda vector, okay? So if you have lambda x, real, okay? D lambda x, this is the gradient, is a line consisting of all the partial derivatives with respect to all the variables in the x vector, okay? And this is a notation that we use, d lambda dx, okay? So a covector field, it looks like a covector, okay? Look, the differential, so the gradient, I would say the gradient, okay? I like this term. So the gradient of a real mapping, defined, so lambda is defined on U. I remind you that U is a subset of Rn. U is a subset of Rn. Okay, so this is just like you have. Do you remember this from Lyapunov? In Lyapunov, V of x was a quadratic, for instance, function. Okay. Okay. So that means dv dx is x transpose p. Is x transpose p. And this is a covector because it's a line, x transpose is a line, times a matrix. Okay. P is a square positive definite matrix, for instance. You remember that from Lyapunov, don't you?
Yes.
Yes.
By the way, have you done assignments 3 and 4? Because I need to grade them soon.
No, I haven't done them.
Okay, fine.
I will be doing them. I think.
But I think assignment 3 is overdue. Assignment 4 is still open. We'll see about it. Okay.
Yeah.
So what is the derivative of some function lambda along a vector field f? That's this one. You remember this one? Also from Lyapunov. dv dx times fx. This is also used in Lyapunov theory. You remember that. We call this the Lie derivative of lambda x. This derivative can be repeated successively. Okay, so LG LF lambda x. That's why you are using this notation because this is easier. LG LF lambda x is d of this function with respect to x times gx. And then if you want to do k times derivative, you use this form. Okay, you use this form. This is called Lie derivative. This is called Lie derivative, like it's written here. Okay, so the meaning of the Lie derivative is it's telling us how the function lambda x, okay, is evolving, is changing along the solution x of the differential equation x dot is fx. Okay, so these are all ingredients, and another ingredient is the so-called Lie bracket. In English, you call this Lie bracket. And I have to write this again because it looks bad. Lie bracket. Okay, this is called the Lie bracket. Okay, note that df dx and dg dx are the gradients of f and g with respect to x. Okay, note that you have the minus sign here. Of course, the Lie bracket has some interesting properties. Okay, you can also do it. And you use this notation. You can also do it successively, k times. We use this notation because this is easier to write with a power k. Okay, the Lie bracket has properties. First of all, the Lie bracket is not linear but bilinear. It's bilinear. Okay, so the Lie bracket of R1 F1, where R1 and R2 are constants, plus R2 F2 and G1 is R1 Lie bracket F1 G1 plus R2 Lie bracket F2 G1. Okay, and also commuting somehow. It's not commuting, but it's anti-commuting. You can try to prove this yourself. So Fg, let's prove it, is df dx f minus dg dx g, and gf is dg dx g minus df dx f. If you subtract one from the other, how much is it? Should be, no, if you add them, actually, if you add them, it's 0, isn't it? You agree?
Yes, it's 0.
So I would write this, this is nicer to write like this. Fg plus Gf equals 0. Okay? All right. We also need the so-called distributions. Okay? So you have D vector fields. Okay? So all these vector fields generate a vector space in Rn. Okay? So this is called a distribution. Okay? It's a bit difficult. I'm not mastering these things very well. But these are very important notions, because these notions help us build nonlinear control theories, geometric nonlinear control theories, okay? Such as feedback linearization. Essentially, this is going to be a geometric nonlinear control theory, okay? Okay. And we have some properties about distributions, okay? What is a non-singular distribution? What is a regular point in a distribution? Okay, it's related to the non-singularity. Okay, any point in U that is not regular is a singularity point. So these distributions are mimicking some sort of function or mapping behavior. You notice that? It looks as if we are talking about functions. True?
Yes.
Okay. Then the distributions have another property called involutivity. A distribution is called involutive if the Lie bracket tau1, tau2 of any pair of vector fields in the distribution is also belonging to the distribution. How are we calling this for linear for linear vector spaces, how is this property called?
For whom? For linear vectors?
For linear mappings. If you have a linear mappings, A of AX, and you also have that AVX is in the same vector field. Let's say call it K. How is this called? You use these properties when you did state space systems. So for distributions, it's called involutivity. For linear mappings, it's called invariance. Invariance. So invariance of linear mappings is somewhat similar to the involutivity of a distribution. Okay, so these are trying to map ideas from this is differential geometry. So these are not constant vectors. These are nonlinear functions, vectors of nonlinear functions. Okay, this is the difference. So the distribution is called involutive. Okay, so a characterization of this property is that a distribution is involutive if the rank of this matrix is the same of the with the rank of this matrix, where here instead of FD you add up Fi Fj. Fi Fj. Okay. Right? This is also very much related. So these notions are related to the notion. So you can define actually. You can define with this. One can define nonlinear controllability using the Lie bracket, because this looks like the controllability issue. You remember that? Matrix R, controllability matrix, B, AB, A square B, up to A to the power n minus 1 B. If you check this out, this R is actually some sort of property like this matrix here. So it's like rank of R. Do you understand what I'm saying? So you can also recover all these things from the linear case. Okay? If you remember how you used to talk about controllability in the linear case. What is a change of coordinates for nonlinear systems? Change of coordinates is something we discussed this last time, is of this form. New coordinate is phi of x. In the linear case, phi of x is tx, t invertible. Okay. So in this case, it's a mapping phi of x. Phi is invertible, so there exists phi inverse of z. Okay. Both phi and phi inverse are smooth. This is more than we used to do with linear coordinate transformations. Okay. Of course, the changes of coordinates are local. They're not global, because we are doing them around some point. Okay. And also, you need, for this mapping phi, to be a so-called diffeomorphism. Diffeomorphism. In English, morphism is with PH. Diffeomorphism. morphism. Okay. So a coordinate transformation in the nonlinear case needs to be a diffeomorphism in the sense that also the Jacobian of the function, you know what a Jacobian is, right? Or not?
Yes.
Not the formula, but
Okay, phi define Rn. Okay, phi of x equal phi 1 x phi n x. Then the Jacobian I can say like this: d phi dx Jacobian is a matrix d phi 1 dx1 d phi n dx1, sorry, dx1. You understand? d phi 1 dxn d phi n dxn. We used this when we did equilibrium points. You remember that? For linearization, for classic linearization. Okay, this is a Jacobian. The Jacobian is a matrix. Okay, so this is belonging Rn times n. This is a matrix. So we need the Jacobian in this case to be invertible because this is a matrix. Okay, so that's what this is, a coordinate transformation. We discussed this last time and I showed you how to apply a coordinate transformation. It's showing here once again how to do that. This is your given system. X dot is fx plus gu, fx plus gxu. You do the change of coordinates z equal phi x, and then you just substitute this into this, you substitute this into you just take the derivative. Okay, so z dot is dz dt, which is d phi dx dt. Yeah, this is the Leibniz rule. Okay, f, you know the Leibniz rule of derivation, don't you? Do you or do you not?
yes, it's the one we also learned in the 12th grade.
Yeah. No, it's not. No, this is not Leibniz. This
It's
is
not the
about
one.
composition, not this one. This one.
Uh,
This one.
oh, yeah.
Okay, is the derivation of the composition rule. This. Okay. So this is what's going on here. This is what's going on here. And then you substitute dx dt. You substitute dx dt. Dx dt is this equation here. It's this equation here. Okay. So finally, you get this. This is the way how to apply a coordinate transformation. Z dot is this one. Okay. Because you need to express now everything in z, because this is all in x. You substitute x with phi inverse. You substitute x with phi inverse. Okay. And substituting x with phi inverse leads to this equation. So this is the new system. It's the same system actually. This is the system written in the new coordinates. In the new coordinates z. Okay. And this is what every mapping f the vector field of z bar, hz bar, gz bar. It's this one. It's this one. Okay. Apply this to the linear case. Linear case. Z equals tx, which means x is t inverse z. Yeah. F bar x is t fx a, and x is t inverse z, right? I'm substituting this in the linear case. Clear? Linear g bar f bar z, g bar z is tb, and h bar z is c t inverse x, t inverse z. You recognize from the linear case? Do you recognize this from the linear case?
Yes.
Okay. Right. So, nonlinear state feedback for single input, single output systems. Okay. So this is nonlinear state feedback. We are talking about local change of coordinates, about full linearization, partial linearization, and some application. Okay. So how do we do the input-output linearization around some point x naught? We successively take derivatives. We successively take derivatives of the output. In time. So y dot, I remind you that y is hx. Y is hx. So y dot is h of x dot. So it's d, like vx, you remember? Vx dot, do you remember from Lyapunov theory? This is an application. It's dv dx x dot. True? Do you remember that from Lyapunov theory?
Yes.
Okay. And let's, okay, so where is x dot here? This is x dot. This is x dot. Okay. Yeah. Okay. This is LFX. Okay. This is LFX. And this is LGHX. LGHX. DHDX times GXU. Okay. Okay. Now, assuming that LGHX is 0, the y dot is L of H. Okay. Who is y double dot? Who is y double dot? This is y dot once again. Okay. So y dot is dy dt. Y double dot is dy dot dt. So it's d to y to dt2. Okay? But y dot is this guy. Y dot is this guy. So we repeat the previous procedure. So y double dot is d, now it's not h, but it's LFH dx times, and this is also x dot. Okay? We know that x dot, this is our system, is fx plus gx u. Okay? Okay. And we get this term because you get dLFH dx times f of x, but dLFH dx is is the derivative, so it's LF2 successively hx through by the definition of the derivative, okay, of the Lie derivative. And then you get the derivative with respect to g of LFH. We also, again, we assume this is 0. Okay? And we stop this this procedure at some point r. So we take the derivatives up to the order r, where in the end this is no longer 0. This is no longer 0. This is no longer 0. R is called relative degree. R is called relative degree. Relative degree. Okay? Do you understand what we are doing here? We take successive derivatives of the output, okay? Yeah? Hello?
Yes, we're hearing you.
Yes.
I
Yeah,
think
okay.
we're
So that's
thinking.
what we do. We take successive derivatives of the output, and we assume these quantities are 0. We assume in the sense that we check, and where we stop with the r, which is called relative degree, it will be explained soon, because it's also related to the linear case. Okay. Now, if you get to this equation, you can build up the linear command. You can build up not the linear, but the command u, and then y differentiated r times in time. It's going to be equal to v. Okay, so you actually build a chain of r integrators. You build a chain of r integrators to get back to the original y. Relative degree, it's this one. Relative, this is an important notion, degree. Okay, a single input, single output system has relative degree r if in some point, so this is also a local notion, if in some point x naught, the following thing happens. LGLF k of h is 0 for any k less than r minus 1. And this quantity, when k equals r minus 1, is different from 0. Okay. Some remarks are in order at this point. Of course, the relative degree depends on the output that you choose. You remember from all the control courses that in general the output is something that we can measure, is something we choose. Okay, it's something we can measure. Okay. There may be points where the relative degree is not defined, so where these things don't happen. Okay. There are output functions, so we have to be very careful because there exists output where the relative degree cannot be defined for any x. But let's take an example now. The van der Pol oscillator, our funny, famous example. We have taken this, we have done this before. We have used it as an example for when we defined types of equilibrium points for second-order systems. And then we also discussed about the Lyapunov stability of the van der Pol oscillator. Okay. These are the equations that define the van der Pol oscillator. X1 dot is x2. It's a mechanical system. X2 dot is minus x1 plus epsilon times 1 minus x squared x1 squared x2 plus u. With epsilon, a positive constant. Okay. What happens if you choose several outputs? This is what this example is illustrating. What happens if you choose different outputs? Okay. Choosing, for instance, the output to be the variable x1, so the position. This is a mechanical system. So if you pick the position, you have it like this. Y dot is x1 dot is x2. So essentially, this is yeah, because this system f of x is x2, and then it's epsilon 1 minus x1 squared x2, and g is the constant 0 transpose, and g is the constant 0, 1 transpose. LFG 0, you see? It's 0 because you get x2, you get nothing with u. So here, LFG is 0. Is 0. But if you take y double dot, you get minus x1 plus x2 dot. No, you get x2 dot, sorry, x2 dot, which is minus x1 plus epsilon plus u. So LFG is not 0 this time. It's not 0, it's 1. So what is the relative degree in this case? The relative degree is 2. What about if we pick the output to be x2, sorry. What happens if we pick the output to be x2? Take the time derivative and the relative degree, because u shows up in the first term, is 1. True? It's 1 because you take one derivative. Okay, so here LFG is not 0. Is not 0. But what happens if you take the output x1 plus x2 squared? Y dot is x1 plus 2x2 times x2 dot. X2 dot is minus x1 plus epsilon times 1 minus x1 squared x2 plus u. U shows up here. U shows up here. So LFG is actually 2x2u. 2x2u. Okay. So the relative degree is 1 again. For all the points which are not 0. For all the points which are not 0. Okay. All right. Because if x2 is 0, then LFG is also 0. You agree? Yeah?
Yes.
Okay. Now, let's do a linear example and see how the theory applies to linear systems. And now we are going to make a short study about linear systems to prove that the theory is the same, essentially. Okay, theory is similar. Now, for linear systems, fx is ax, gx is b constant matrix, hx is cx linear mapping. So LFK times h is CAK. Why? Because LF so LFH is DF dx times no, dH dx, sorry, dH dx definition, yeah, times hx. Okay, but hx is this guy, not h, sorry, fx. Damn it, fx. Okay, and so essentially, fx is this guy, hx is this guy. So what is dH dx? What is dH dx? Hmm? What is dH dx?
It's C.
Can you repeat that, please?
Isn't it C?
Of course, it's C. So this is C times, and fx is ax. It's CAX. So LF2H is LFHX. So this is D CAX dx times AX. So what is this? How much is this? What is the derivative of CAX with respect to X? It's a linear mapping. So what's the derivative of CAX to X?
CA.
What?
CA.
Of course. So this is CA square X. And this is proving this relation. The same applies for this relation. Okay? Yeah? So LFKH is CA to the power K times X, and which means LG LFKH is D LFKH to dx times G. What is G in this case? G is the constant B. Okay? So this is what? CAKB. True? True. Okay. So the relative degree is what? The relative degree is said to be that all the LGs accumulated like this in K are zero, Okay, 0, and then c to the r minus 1b is not 0. Okay, this is if you check this out, the relative degree is actually the difference between the nominator and the denominator of the transfer function hs. How do we call this in the linear systems case, the difference between the nominator and the denominator? How do we usually call this?
The zero pole axis.
Exactly, pole zero excess.
Pole zero axis.
Yeah, so this is actually ER in the linear case. In linear case, R equals E. I write it in Romanian, excesul pol zerouri. Okay? This is what a relative degree is for a nonlinear system. Okay? Yeah. Okay. These are the moments of with respect to infinity of the. These are from the CAKB. I'm just trying to remember. These aren't from the Hankel matrix. Yes, these are from the Hankel matrix. Anyway, okay. So the relative degree is the pole zero excess of a transfer function. Okay. Okay. So now you check this in the linear case. We take a controllable canonical, the controller canonical form of the transfer function given by these two polynomials of a strictly proper transfer function. So we assume this transfer function is strictly proper. So the m degree of the nominator of the nominator is strictly less than the degree of the denominator. Okay. So this is the controller canonical form, if you remember from last semester and from the second year. Okay. Because if you remember, we studied these things again last semester at the reduction model reduction course. Okay, so this is the controller canonical form. Okay, so usually what you do is you fill up B0 BM, and then you fill up with zeros. You fill up with zeros. Okay, so CA is this one. CA to the power n minus m minus 2 is this one. So it's you see, if you see these coefficients, they just shift along as you increase the power. If you multiply these things with b, CAB0 and so on, but this one is b. So the relative degree R is n minus m. And this is the proof. This is equal to E. Okay? This is the proof. Is it difficult? Is it difficult?
It's okay.
It's okay, huh? Yeah. In the linear case, things are easier. It's true. I agree. Okay. So what happens if you have relative degree? What are the consequences of computing a relative degree? If you have all these derivatives, so these are gradients of these functions in the point x0, they are linear independent. So usually if they are linear independent, then R is less than or equal to n. Okay. Now if you just do this notation with phi of these functions, we can always pick n minus r functions such that phi equals to these things with a Jacobian non-singular in x naught. Okay, and the rest of the functions, so the functions that you pick from r plus 1 to n, they can be chosen. So you can usually choose them for free. Okay, so the first r functions are this, and the rest of the r functions can be chosen for free such that this property holds. Holds. Now, what happens if you do the representation in the new coordinates? Look what happens. The new coordinates are very nice. So z equals to phi x. Okay? So dz dt is d phi 1. So these phi's here are used to build the coordinate transformation. Okay? Okay? They are used to build the coordinate transformation. Okay? So this is how to build a coordinate transformation that brings up the system, that builds the system in a very nice form. So if z equals, so this is z equals, okay? I should write here for simplicity. Z equal phi x, okay? Z equal phi x. So now if you substitute, you get this form, dz1 dt. z1 equals phi 1. So d phi 1 dx dx dt. But what is d phi 1? What is d phi 1? d phi 1 phi 1 is hx. So d phi 1 is dh dx f. So this is the Lie derivative with respect to f of hx. But this is phi 2x. So this is z2. Agreed? Is it true?
Yes, it is.
Okay. Now you just keep on going like that, and you end up zr dot is zr. But zr now is this guy, because this guy is no longer 0. This guy is no longer 0. Okay. And if you know that we said we are picking these functions such that this is true. This is true. So dzi dt is lf phi I x, is lf phi I x from r to n, from r to n. Okay, so now you can get the so-called normal form. You can get the so-called normal form. So this was what happens from z1 to zr minus 1. This is zr, which is going to help us to compute the feedback linearizing control law. These are zr1 to zn dot, and this is the output, z1. So this is the form that we have brought our system into. Okay. Yeah. Okay. And now we have an example. We have a nice example. We have the DC motor. DC motor. We have the DC motor. Okay. Very nicely defined here. These are the electrical. Equations, and this is the main equation. This is the mechanical equation, the rotation, yeah, because the rotor is rotating to build power. Okay. This is the mechanical equation, the slow equation. This is slow dynamics, fast dynamics. V is the voltage, I is the current, L is the inductance, R is the resistor, omega is the angular speed. I should write these in English for you to have it easier to understand. So voltage. Okay, current you know, inductance, resistor you know, angular velocity. inertia, friction coefficient, okay, and this is torque. This is torque, okay. This is torque. The output, the input, sorry. It's usually a disturbance. The torque is usually disturbance. Okay, it's an input anyway. So the assumptions we are working with. So we have a constant input. We have Bm equal to 0. So you have no friction. No friction. The disturbance is constant. The input is U equal to Vs. So this is the input. This is the control input, and this is the disturbance. So this is U, and this is D or W. Okay, if we use control notation. States X1 is the current IX, X2 is the current IR through the resistor, and X3 is the omega, the angular speed. And the output, of course, we need to measure, because that's what we can measure using using a speedometer. We can measure the angular velocity. The rest are states because we cannot measure them. Okay, we cannot measure them. We make some notations of the coefficients. These are some coefficient notation. Okay, so we can have an easier way of understanding these things. Okay, yeah. Okay. Example. So we continue the example. We've got the 3 state equations, and we've got the output, we've got the input and the disturbance. Okay. Right. If there is no torque, so there is no load. I didn't remember this. Load. Okay, Sarchina. Load. If there is no load, okay. Is it easy for you to follow me in English reading these notes in Romanian? Can you follow?
Yes, it's okay.
Okay, fine. So what are the equilibrium points? The equilibrium points are of this form. It's not hard to compute. You set everything to 0. You set everything to 0. Okay, x1 is 0, makes sense. X2 is tau is theta 5 divided by theta 3. Theta 5 divided by theta 3. Why? Oh yeah, because you do the derivative here with respect to x3. And here you take the derivative, you take the equation with respect to x2. Okay, so you get omega. I'm trying to understand the equilibrium point computation. So from this equation, it's clear. This equation is clear. X1 star equals 0. Okay, so this is 0. This goes away. And then you have 0 equals minus theta 3 x2 plus theta 5. Oh yeah, that means x2 star is theta 5 divided by theta 3. It's correct. And in the last equation, okay, in the last equation you have 0 equal theta 6 x1 x2. Theta 6 goes out, so 0 is x1 x2, but x1 is 0, so you get 0 x2 equals 0. Yeah, but x2 is, I don't get it. Why is x3 omega? Oh yeah, because x3 is not coming into any equation. Yeah, okay. So x3 is any constant. Okay, so all the equilibria have this form. All so any constant angular velocity is an equilibrium. Is an equilibrium if the engine is just if the rotor is just rotating. Okay. They tell us that around such an equilibrium point we have relative degree 2. We have relative degree 2. Probably you take y dot. Y dot is x3 dot is theta 6 x1 x2. Y double dot is theta 3 theta 3. What am I doing here? I'm not doing it properly. Y double dot, oh yeah, sure, I'm an idiot, is theta 6 x1 dot x2 plus theta 6 x1 x2 dot. You agree? So this is theta 6 times x1 dot, so that's minus theta 1 x1 plus theta 2 u plus theta 6 times x1. Oh, I should have here x2. I forgot. You agree? Right. Theta 6 x1 times minus theta 3 x2 minus theta 4 x1 x3 plus theta 5. And apparently, because u shows up here, theta 6 x1, yeah, sure, x2 equals 0 around this equilibrium point because x1 is 0, you see? In this point. In this point. So this is 0 because here you can have x1 star, x2 star. Okay? This is 0. So, again, no u term. And then you take y divided 3 times. Good Lord. Who is going to compute this derivative? Let's just believe him. Okay? You see what I'm saying, right?
Yeah.
It's kind of difficult to compute these things.
Yes, it is.
Nonlinear systems is not easy, but you can do this exercise yourselves. Okay? You can do it yourselves. Right. Okay. And then he tells us, if you remember, we can build a coordinate transformation. If you remember, we can build a coordinate transformation, which is this one, z, which is this one here, z, where we take phi1 hx. Let's go back here. So phi1. Oh yeah. is hx. This is hx. Oh yeah, and this is the phi x here. Here you build the phi x. Here you build the phi x. Okay? And you get the normal general form. Okay, you get the normal general form. You just need to substitute these coordinates and to try to compute this yourselves. Homework. Okay. Because now you just need to substitute this into this. You substitute this into this. Substituting a coordinate transformation. A coordinate transformation. Okay? Okay. Yeah. Okay. If you do not choose these functions to have the property that LG, LG, LF using these phis are not zero, so you choose them any functions, you get this. This is already fixed. This is already fixed given by the relative degree. Okay. And this is what is left. This is what is left. Now, because they are general, they also create because they're general, they also create a dependency on U, which is this one. So this is more general than what you have seen before. And an example is this one. You have this nonlinear system. You have this fourth order nonlinear system, good heavens, which has a relative degree in all points x3 which are not -1. And the global coordinate transformation is this one. Okay. Because he's picking the rest of the functions to be just anything. Okay. And if you substitute, you need to substitute this back into this. Okay. And see what happens. We can have full linearization. So full linearization via state feedback. So full state feedback linearization. Full state feedback linearization. Okay. So for r equal to n, so when you have n, n poles and no zeros, yeah, this is in the linear case. In the linear case. N poles, no zeros, no finite zeros, of course. You can write this in this form. Oh, by the way, I was just asking you, when are you going to pick up your papers for the exam? Irina has picked. Diana has picked.
I'm going to send you a message today.
You do that because listen, who wants to start presenting and do the exam now? You can present next week. We can start doing the exam from next week. You don't need to come, all of you, on the 9th of February. If you want to do it before the exams, we can do it before the exams. Next week and the next week. Do you understand what I'm saying?
Yes, I also
Yes, it's
my paper ASAP.
Sorry?
I'll also pick my paper as soon as possible.
Okay, please do that as soon as possible, all of you. Because starting next week, who's ready by next week, you can present. And we can discuss. Okay. So this is full linearization. So if the relative degree is actually n, that means you have n poles and no zeros. In the linear case, it's something like this. Okay. For such a function, this is the normal form. This is the normal form. But you recognize this from the linear systems, okay? So when you have HOS is 1 over Sn plus an minus 1 s to the power n minus 1 plus a0. This is usually y of s over u of s. Yeah? Okay? So if you know that the product of this diagonal is equal to the product of this diagonal from simple math. You agree, right? So this means that s to the power n ys plus a n minus 1 s n minus 1 ys, okay, plus a0 ys, okay, you agree, equals us. True? Okay? You know this, right? Then, if you take Laplace inverse, because you can do that, but be careful that you come back with Laplace using initial conditions. Initial conditions, this is in English. Initial conditions 0. Okay. This is what? Y n of t plus a n minus 1 a the time derivative n minus 1 times t plus a0 y of t equal ut. You remember that? Laplace transform and Laplace inverse. True? Hmm? Right. So how do you build this into a system of this form? Into a system of this form. How do you do this? You do this using what you used to do in the second year. Y of t notation x1. That means that x1 dot is yt dot is x2. That means that x2 dot equals y double dot t is x3. You remember we used to do that? And so on. So xn minus 1 dot is y n minus 1 t equals, no, and all of these are notations, xn. And the final one, because yn of t with derivatives taken n times is minus an minus 1 y minus 1 minus a0 y of t plus u. True? So xn dot is minus an minus 1 xn minus 1 minus a0 x1 plus u. You agree? You
Yes.
agree? Okay. I think here is just xn. Sorry. No, it's okay. Oh yeah, it's xn. Here it's xn. This is something you used to do. This is something you used to do. So in compact form, if x equal x1 down to Sn, then x dot is 1, 0, 0, 0, 0, 1, 0, whatever. Okay? No, sorry. Mistake. No, it's 0, 1, 0, 0, 0, 0, 1, 0. And then if you go down, this is 0, 0, 0, 1. And the final line is minus A0 minus A1 minus AN minus 1. X plus 0, 1, U. So do you recognize the normal form? This is where it comes from in the linear case. From the simple nth order differential equation. From the simple nth order differential equation. Agreed? Is it similar to what they do here? It's similar, okay? But now what happens? Because you have this, the Zn, okay? The Zn, if you take this command, if you take this control law, you get a linear controllable system. You get a linear control. This is controllable. It's easy to see because you have one here. It's easy to see because then successively the control goes up to the first variable. Okay? Because of this, because actually you can rewrite your normal form like this. But since all of these are zero, in our case, 0, 0, you get you actually get yn equals u. Okay? You get yn equals u. Okay? So what are the conditions to apply full feedback linearization? You need to have the output hx with a relative degree equal to the order of the system. It's not only sufficient, but it's also necessary. So it's necessary and sufficient. This is wonderful. This is necessary and sufficient. Okay. So if you have an hx, if you pick, because hx is something you pick, if you pick an hs, okay, which is necessary and sufficient, with a relative degree n, if and only if you get the full feedback linearization. When do we have such a function? Such a function exists when these conditions are fulfilled. Note that here you have an involutivity condition, an invariance condition, like you do in the linear case. Okay. I would really like to ask you to what are these conditions? Homework. What are these conditions? Coming down to for linear systems. It's probably about the controllability, right? So here, and after that we stop, we have a procedure for full feedback linearization. You start from fx and gx, you build these vector fields as described here, you build these vector fields as described. These are Lie brackets. These are Lie brackets. This in the linear case, please show me that this is actually the controllability matrix R in the linear case. Try to prove it yourselves. If these conditions are satisfied, then you solve this equation, okay? And then you compute these terms, alpha and beta, and this coordinate transformation. You apply the coordinate transformation and you get the feedback linearized, the fully feedback linearized system. Okay? Agreed? It's not very easy, but if you check the linear case, oh, shoot. If you check the linear case, okay? If you check the linear case for these things, maybe you can understand a few things, okay? Yeah? Okay?
Okay.
Have you got any questions, please? Any questions, please?
Not from me.
Anyone else? Anyone else?
Oh, sorry, I was disconnected for a couple of minutes. What did you talk in the last minute?
I was showing about the procedure to do full feedback linearization.
Okay.
This one on this slide. And I was telling you to do a homework and apply these things to a linear system. And tell me what the conditions are for a linear system. What these conditions come down to for a linear system, okay?
Okay.
And then I was telling you, I was asking you if you have any questions. So I kindly ask you to please pick up papers. Tell them which papers you have picked up or you picked up. Please do the report. Okay, you can do it handwritten. You can do it in a short presentation, but you need to explain to me what's going on there. Okay, and then please do the simulations. For the exam, I'm going to look at the report, and you need to tell me what the simulations do. We'll do some sort of oral exam.
But I think not all of them have simulations.
Are you sure? Okay, if they don't have simulations, we just talk about the paper.
Okay.
But try to pick or try to build up something. Maybe you can simulate something from those papers.
In fact, can I tell you now what paper I would like? Because I
would like you to have it written somewhere, because
okay.
Just write it on the group or write it in Teams. Write some or send me an email or something, because I need to remember.
Yeah, I'm writing now on WhatsApp.
Okay, you can send me a message. Okay. And starting next week, okay, don't forget to do assignment 4. I'm going to grade the assignments. And okay, the grades are, so the final grade is 50-50. 50 points assignments, 50 points the paper. Okay. And in those 50 points for the papers that have simulations, the simulations count. Okay? Do we have a deal?
Okay.
So you can start presenting from the next week. I don't mind, before or after the lecture. Okay?
Yeah.
Right.
Sure.
So if there's nothing else, we can stop here.